Let me see. Hello.
Yes, sir.
Yes, sir.
So how many of us have joined? I cannot see the screen.
32, sir.
Okay. Okay, let me start the class. Let's see. So in this class, I'll be talking about multi-threading or how to use threads. How to use your class নিচ্ছি না class নিচ্ছি মুশকিল হবে So we'll start with real world analogy of threads, definition of threads, possible applications, then possible implementation of threads, and the use of POSIX thread library. We'll write some codes if time permits. Okay. So let us take the analogy of what we generally face in our real life also. So we have got the department of earlier, I mean before 2017, we had two departments, separate departments. One is department of CSE and one is department of IT. And the department of IT was in that main block. So and we used to run two programs. One is BTech CSE and one is BTech IT. Okay. So it was running fine, but then what we found is the laboratories, say for example, are more or less the same because there is lot of overlap between BTech CSE and BTech IT. Then there are I mean the faculties also sometimes you know that their expertise are also the same. The curriculum is also there is a huge overlap of the curriculum, but still because of some reasons the department of IT started in 2000 and the department of CSE it started around 1990. So both coexisted even though there is a lot of overlap, and because of this because of two separate departments, the having a separate department means you have to have separate staff, separate faculties, then separate HODs, space, everything should be the same. And generally although the laboratories they have got the same purpose, but a CS department class sessional cannot be taken in the IT and vice versa because there are obvious reasons. And even if the laboratory is remaining is lying vacant or idle, it cannot be used. So hello, am I audible? Can you hear me?
Yes,
Yes, sir.
Yes, sir.
So what happened after 2017? Now noticing this huge overlap in the functioning, in the curriculum, in the content, in the maybe the uh, laboratories, whatever. So there was a proposal that was came from the administration that these two departments should be merged. And I think when you were in the first year, you probably noticed that the IT, the BTech IT was the final year batch. I think BTech IT was no, I think this year it was the final year batch. And after that, this BTech IT program was, I mean, it was taken off, and instead of an intake of 100 here and 100 here, now we have got 200 intake in BTech CS. So that's a different story. But the point is, for some amount of time, like from 2017 to 2020, this what we had, there is a department of CSE. There is a single department with a single HOD and the staff, common staff. The classrooms, the laboratories are all the same, but both but the same department ran two different programs. Now there's a distinction between a program and a department. Okay, because there is a lot of overlap in the programs which are of similar type. So two departments are basically merged. It is not that the IT department was abolished and the CSE was there. It was basically merged because the same IT faculties, they joined as a CSE faculty. So they are all converted to the same department, and might have we could have used a different name for the department, but fortunately we have the same department. It could have been named as Department of Computer Science, like that. So what I wanted to specify is that the maintenance, why these two got merged, because the maintenance overhead is much reduced and much less, and maybe in near future this staff strength will be reduced. Okay, because you don't have to have separate entities. There is one HOD who can manage all this. So this part is pretty clear. So if there are two things running in parallel simultaneously, but if there is a lot of overlap, so you could have reduced the overhead by still having it running separate simultaneously, but not as a completely isolated entity. Okay. So now let us see the analogy with the computational environment. Here is a parent process. Here is the parent process, and we have got two child process created, child 1, process 1 and process 2. And probably you can recall the kind of assignments that I given earlier, that if you have got an array of numbers, you take an array of numbers, and within that array there you create so this parent process creates two child processes, and one child process will basically focus on searching or maybe finding out something in this range, and the other child process will focus in searching or operating in the remaining portion of that array. So there is a single array of integers which probably we have input in this parent process, and in the parent process data segment it is there. Now when the parent creates two child process, so automatically what we know that the child will start with the same content that it was there in the parent, right? Hello?
Yes, sir.
Yes, sir.
So that we all know, and not only that, the child will have the same file descriptors as the parent. It will have the same data segment, it will have a separate copy, separate space, but the contents will be simply copied here and here. The code segment, it will have a separate space for holding the code segment, but it will have the same content, and same holds for the rest of it. So basically when the child processes are created, it will be created as if it is a kind of clone of the parent, but it will have its own entity identity. Now why the parent created these two child processes? Because the parent says that if I do the it may be a very long array, and if I create multiple child processes, I know that or the as a programmer we know that each of the process, it's a child process or parent process, each process can be scheduled separately. So the unit of scheduling is a process, right? It may be a parent or a child. So if you have created multiple child processes, you can probably take the advantage of running the code simultaneously. If you have got say multiple CPUs, so the idea is instead of, so if you have got a single CPU, there is no probably no gain. But if you have got multiple CPUs or multiple cores, CPU core, say 4 or 8 or whatever, 2. So in creating multiple child processes, probably can speed up the execution, right? Hello?
Yes, sir.
Yes.
That was the intention. Now in doing so, now it was running. I think almost all of you have solved the problems, and you know that separate child processes were created. They started with the same state, and then accordingly they just did it. So in this case, the data segment or the global array, nothing was changed. So they just access and they just do some processing there. That's all. So, and I know that most of the contents of the parent and child are the same, right? And even in this case, the code is also the same, more or less. The logic also is the same. So your question is, can I do something similar that we do generally in a real world problem, like merging of CSE and IT departments? and having a combined having a single department running two programs simultaneously. So got the analogy here?
Yes, sir.
So now, so once we know that it is something different from this one, so this is different from this. So now this parent process, so this parent process we say that, so now we say talk about a different terminology. We say that it's a parent process thread. Now creates two threads, child thread 1 and child thread 2. And once these two are separate threads under the same process, so the process is the same and we have got two threads. So we expect some kind of lightweight, so we expect that these two threads should have something in common and they should also have something exclusive to each of them, right? As like in case of the programs, the BTech programs, we know that this portion is common. This portion is common to both the programs, BTech CS and BTech IT, but precisely speaking, the curriculum is not exactly the same. They might have different set of electives. They might have different some bit of subjects that got changed in the final year or pre-final year. The fees might be different. Class routine also will be different. So like that. So they will have something of their own, unique, and there should be something that they can share. Same in this case. You see, we know that the same the global array which contains the actual data, we need not have to copy in both of it, right? So if it is a thread, if we call it as, so the original thread, if we call it as a parent thread, we'll have the data segment common. That means everything that you declare global will be shared by both the child threads. The process control block, or I mean, so you say that this outer box is a process block, or it is a process representing a process, and these inner small boxes are representing threads within that block or within that process. So this is a process and these are threads within a process. So to maintain a process, we have to have PCB. So that is a single PCB, and the file descriptors, because they are all the same, so it will have the same data segment, code segment. So everything will be the, so this will be the same. But the only difference is here. So these underlined ones will be different. As you can see here, the user and the kernel stack is different. Program counter is different. And the scheduling parameters are also different, because now these threads are individual executable entities, right? So if I have created these threads, so how many executable entities will be there once I create two child threads in the second case? Hello?
Sir, total three, because child one,
Parent
child two, and parent.
process and the
So,
other two
so you
threads.
can say the parent thread and there are two child threads. So total will be again 3, right? So here also it was 3 in this case, and here also it is 3. But so you basically can exploit if you have got 4 CPUs or if you have got 8 CPUs. So you can really exploit the presence of so the distinct CPUs that are present, right? By creating separate executable units. But here the executable units are processes by themselves. They are heavyweight. Heavyweight means each of them, they will have all these things of their own. But in the second case, you still have 3 executable units, but these 2 units are basically lightweight. We can say they are having, they are not as heavy as that of a process, because they only are differentiated in terms of the stack, both the user and kernel level stack, then the process program counter and the scheduling parameters, because you have to have separate scheduling parameters for each of them, because it's a different executable entity, it's a different executable entity. So you can have different scheduling parameters that you can define for each of them. And why you require a different stack, user stack? Why you require? Because when you execute a function, or when two units, two executable units are assigned a CPU, so they will have their own trajectory, right? They will have their own logic and own way of doing things. And whenever you are trying to execute something, maybe a module or a function, then you need to have your own user stack, right? The user level stack need to be separated.
Yes, sir.
Otherwise, you cannot really because execution means what? Whenever you are executing something, user stack is essential. And if that execution goes to the kernel level, then it uses the kernel stack. So the stack need to be isolated, need to be separated, and they must have their own stack. And because they are executable units, they should have their scheduling parameters. And what else you need to have? Like maintaining a thread, the information of a thread, you have to maintain the information of this, like maintaining the information of a process which is done using PCB. Now, to maintain the information of a thread, you need a TCB, thread control block. So this is also, so this should be TCB, right? Thread control block. And again, as like we have defined the state of a process, like running, suspended, then ready, and all this. Now, each of these threads also may be in a different state of execution. So maybe that this thread 2 is waiting for some event to occur or some input for your own input. But thread 1 is running because it has received. Okay? So, or maybe both are running, or maybe both are suspended. So each of the thread need to be specified. I mean, we have to maintain the state of each individual thread of execution. Is that fine? So if we look into this, I mean, compared to this one, to the left side and the right side, we can easily say that these threads are, in some sense, we can say that these are lightweight entities or lightweight processes. Why still we stick to the term process, lightweight process? Because we say that process is the most fundamental executable unit. But now this is not as heavy as of a process, so that's why we call it as a lightweight process. Okay, so if we do so, if we can really implement this idea, so then what will happen? The creation and the switching of threads will be much faster. Say if the same, say the CSE department, it wants to say start a program BTech in data science, say for example. So now if the policy was to just create a separate department for the data science, so data science department of data science, and then you open a BTech in data science, that will be much overhead, because you have to immediately find out a space, a departmental space which is not overlapping with other departments. That is the first thing. You have to probably recruit some, at least few number of faculties. You have to recruit some staff. So everything will be repeated. But if you can make it as a part of the computing existing computer science department, then you can say that, okay, let us start with the existing resources, but let us start as a separate entity. You will have a separate admission for those students, separate eligibility, everything will be different, but the same set of faculties, because there is a lot of overlap. So the same CSE faculties, some of them may actually take the responsibility of running that particular course, right? So creation of a new process, and whenever you are creating a new program within a particular department, the getting the permission from the ministry and all this becomes more hassle free. I mean, much more uh, less hassle of it. So everything will be different. So is that part clear? The basic need, why we require a thread, and what is the analogy to the real world?
Yes, sir.
So now let us get into the technicalities. So thread in OS definition is multiple strands of execution. Multiple strands of execution in a single program are called threads. A more precise definition is that a thread is a sequence of control within a process. A thread is a lightweight process. I think you all agree with whatever it is written as a definition. We just now mentioned it. So because creation, termination, scheduling, switching among threads is much less than that of a process creation termination set. So why it is lightweight? Because creation, termination, scheduling, switching, all the aspects. I mean, maintaining a process or maintaining a thread is of less overhead compared to maintaining a process. And multi-threading is the ability of the operating system to support multiple concurrent paths of execution within a single process. So what we specify right now, what we mean is right now is earlier one process means one thread of execution. So you really cannot make a process, I mean, parts of a process or components within a process run simultaneously. That was not possible earlier. But now you say that
Sir, you are not audible.
Hello? Hello?
Yes, sir, audible.
Yeah, sorry. Because of power problem, went off completely. Okay, just a minute. I guess it is visible.
Yes, sir.
Yes, sir.
Okay. Yeah, what you are discussing. Uh, so multi-threading is the ability that the operating system can support multiple concurrent paths of execution, and process can just create a single child thread instead of creating a whole new child process, and multiple threads of a process which share process control block, code segment, data segment, file descriptors, and current directory state. Okay, and also signal handlers. So the previous ones it's fine, but what about the signal handlers? What does it mean? What does it imply? That multiple threads will share the same signal handlers. What that actually means?
Sir, sir, if one of the threads receive any signal, then they are applicable for all of the threads.
So signal handlers means if for control C, that means SIGINT signal, if a particular thread says that I would like to ignore, so that handling routine will be applicable to all the other threads. So the main problem is one thread says that I would like to ignore, but the other thread says that for the same SIGINT I would like to get terminated. So that is not possible. Is that fine?
Yes.
So they are somewhat, in terms of the action, they are almost tied. But multiple threads of a process maintain separately these following things. That is TCB. Why TCB is required? Because like processes, now you have to maintain and track the details of a thread unit within a process. So for that, you can always define a specific data structures, which is a thread control block. And as I mentioned, for the local variables, because whenever you have a separate execution, the local variables might have different values. So maybe both the threads are executing, say, some function, uh, say for example, matrix display, or maybe matrix addition. So both might be using the same, but they should have the separate copy, because it may happen that in the thread one, the matrices are multiplied only the first row and the second row, but the second thread, it has somehow got scheduled faster, and it is now multiplying, say, the fifth row and the seventh column. So those values of I and j need to be separately stored. So that's why each thread need to have their own local variables, that means own stack. The stack size also might differ. The scheduling priority can also be changed, so that because you are treating them as a separate executable entity. So so you should be able to tune the priorities to a certain level, right? And the state information, definitely that will differ. And the signal mask. So signal mask means what? So signal handlers are the same, but signal mask may differ. What is the function of signal mask?
Sir, uh, sir, it's a vector where it's a bit is set to one if that signal has come.
Yeah, that means say particular thread, say the thread one may decide that I would like not to receive these signals if they are allowed to, but thread two says that I would like to receive all the signals. So they are free to say that I would like to. So the masking of the signals, that bit vector or whatever, that is separately maintained by different signals. But once a signal is received, then handling is all the same, irrespective of the thread uh, in a particular process. So to summarize, individual threads can block signals. I mean, one can block, one may unblock, but when when a particular thread modifies the action associated with a given signal, all the threads share the same action. Is that okay?
Yes, sir.
So now these are some say figures. I think these are from the book by Silverstad and Galvin. I think I can ignore it. So threads in operating system. So what happens? So thread, now you can say the thread is a unit of resource ownership, is referred to a process or task. So the unit of resource ownership is referred as a process or task, and the unit of scheduling is referred as a thread. Do you agree with this? So when you say that resource allocation, it is done with respect to a process to another process. But whenever you say that scheduling, what need to be scheduled? A particular thread within a process need to be scheduled. Okay. Now, if a process has not created multiple threads, you say that, okay, one process, and within that process there is a single thread. You can say like that. So once you have considered that the operating system is multi-threaded, now you say that the basic unit of scheduling is a thread, not a process. And the trivial case is a process is having just a single thread of execution. Is that fine?
Yes, sir.
Now multi-threading is mainly useful in multi-core processors. Now you say that hello.
Yes, sir. You are audible.
Yes, sir.
There are always these disturbances. Okay, so multi-thread. So whenever you have got multiple cores, I mean multiple processor cores, only then you can make use of the existence of multiple threads. So if in a machine you have got a single core or single CPU, then even if you have got multiple threads, probably that will not be very much useful, right? So the only thing can be so can you say that when can you say suggest an instance when this will be useful? You have got a single processor or single core processor, and you have still a process has created multiple threads. Now, can it still be useful in some cases? What my question?
Sir, overhead size will be smaller.
No, not overhead. Say for example, I have created multiple threads. Now one thread is going to take the input. So for taking the input, I have got created one thread. One thread is just doing the computation part. One thread is doing the display part, or maybe writing it to a file part, right? Got the point? So
Yes,
now
sir.
writing it to a file, I mean, it does not involve too much of CPU. So two threads are involved in IO. One is input output, one is doing the file input output, and one is just doing the CPU. I mean CPU execution, the core execution of it. So if you do so, then even if it is even if it is a single CPU, probably you can exploit the presence of multiple threads. Otherwise, what happens? The same process, when it goes for IO, the computation cannot be done, right? But if you have created a separate thread which can compute if the data is ready, maybe you are reading in, so there is stream data is coming one by one, and there is another thread which is taking the data and processing it. So in that case, even if you have got a single core, probably creating multiple threads can still be beneficial. But whenever you have got multiple cores, then creation of multiple threads can really be, something great, right? It will really speed up the applications, the processing speed of the applications. So we'll see that we'll write the code and we'll see that. So communication among threads. Now, so we have already found how the processes communicate with each other. How they communicate? Processes.
Signals.
So signals.
Hmm? Using signals, there is one way. Now there are many other options also. You'll see that. But communication across threads is also becomes easy. Why? Why it is easy? For simple reasons. Say when we are the CSE department and they were the IT department, like Sajol Mukherjee. So he was basically a IT department faculty. He belonged to IT department of IT. Who is taking your compiler class for he was originally belonging to the he belonged to the computer applications department, MCA department. There was a department called MCA, right? So now earlier, if I would have to say officially communicate something to say any of these two faculties, what I would have done? If I would like to officially communicate something to them, what is the protocol? We are from different departments. What should be the protocol? Any letter or any official communication should be routed through the HOD, right? Getting me?
Yes, sir.
Yes, sir.
But now once we all belong to the same department, so there is no official protocol. I can easily say that okay, you do it, or can you take my class? But earlier, if I say I would like to I would like not to take the class, I cannot simply ask Subhrojit, okay, if you want you can take the class. It is not possible. So that would have taken a long official protocol communication and all this. So communication among the threads becomes very easy. So in this case, in case of threads, what is the easiest way of communicating among threads? What do they? So they share something in common. So then that can be exploited. What is that?
So
Data set.
global variables.
Yes, global variable they are sharing. So it's something like you have got a common notice board, right? So in a common notice board, if you place something, if you write something, so the CS BTech CS students they can see, BTech IT students also they can see. Or if the BTech
So
IT
your
students
voice
write,
is breaking, sir.
hello, hello.
Yes, sir. In between, your voice is breaking. Now it's okay.
Yes, I know because there is some the power is not there, and I have to use my I have to tether it from my smartphone. So I don't know. So got this point. Why it is easy? And earlier, when we considered communication among processes, how do processes communicate? One is signals, another is using shared files or using shared memory. So it is by default no memory is shared among two processes. So if I would like to do so, I have to create a memory segment which is tagged as shared among multiple processes, right? Hello?
Yes,
I
sir.
am not sure whether I'm still audible. That's why I'm asking repeatedly. So thread communication becomes unsafe. Now the thing is the ease of communication. You have to you get it, but at the cost of some additional overhead. What is that? So whenever you are say in case of two programs are getting say are running under the same banner of a department, so communication becomes very trivial. We all know that. So the same HOD posts the message and notice, and both the programs the students they can see. Fine, but now this communication may lead to some unsafe outcome. So whenever you are having, so we have already found that, right? So if you have got a global variable which is called as a account balance, and if multiple threads are trying to modify, some of the thread is trying to update, some is trying to increment, some are trying to decrement. So if you don't have any primitives or some mechanisms to have a consistent access, so what will be the case? This ease of communication may lead to inconsistency. Okay. So thread communication must be must take care of proper synchronization primitives like semaphores and all. Fine.
Yes, sir.
Huh. Okay. Now thread libraries. So earlier in the so we know that the Unix operating system that was so people started writing it in the 80s or mid 80s. It was almost got published and publicly it was available and anybody can use it. The BSD specifically. Now, during that time, there was no concept of threads. So people were happy, the designers were happy just to provide the facility to create multiple processes. That's all. And whatever we have done till now, it's good enough. It was good enough. Because those days you cannot simply think of having a quad core, say desktop. There was no desktop those days. I mean, desktop in the late 80s and 90s, desktop became popular, and operating systems like Windows, and maybe sometimes you have got Linux also installed uh, in the desktops. So no question of having multiple cores. Affording one single CPU chip is it's too costly. Sometimes you have got servers which used to have say 2 CPUs or maybe 4 CPUs, but they are too costly servers, cost in terms of lakhs those days. So the need was not there. I mean, it was quite okay, and people were quite happy. Designers were quite happy with having multiple processes, and even though they are heavyweight, nobody cared about. Now, during the 90s, what happened? Now people realize that probably it's of no point of having such a heavyweight entity of for scheduling, and we should now, like the concepts that we are talking about, people got really bothered about this, and they thought of doing something different, like creation of the threads. So these thread libraries started appearing from the mid 90s. Okay, so 95, 94, like that. And once it is there, now so the basic problem was like Unix, or the basic philosophy of underlying philosophy of Unix was implemented in multiple in multiple organizations that we found in some lecture. I think you can recall that there was BSD, there was Sun Microsystems, there was then Apple also developed something. Okay, so Minix was there. So there are so many implementations of the Linux Unix philosophy. So something need to be standardized so that if I write a code in the Linux and if I run it in some other operating implementations of Unix, it should have run. I mean, I should not bother about so anything that is Unix like, my program should run. Now who is going to ensure it? So for that you have to have a standard interface for implementing threads also. So if you have a threaded application, multi-threaded application written, so that multi-threaded application you must be able to run it irrespective of the kernel type, or irrespective of the implementation type and all this. So it must run in Red Hat also, in Ubuntu also, or maybe in different versions of Ubuntu and like that. So to enable that, to ensure that a portable operating system interface, which is in short called as POSIX, was you know that that standardization came from mid 90s. Okay, and things gradually started becoming standardized. I mean, in fact, in our college days, it was really difficult. You really do not know, if I write some code, what is going to happen. So if I wrote it for BSD, it will run only for BSD. If I try to run it in IBM AIX, IBM's version of Unix, it may not run in some cases. So there was a big headache. Now once this POSIX came, now people were happy. So if you follow something using POSIX standards, if you have got a function interface using POSIX, now internal details will be taken care of. And for the threads, because the POSIX standard also, POSIX is not only meant for implementing a standard for threads, it is for implementing a standard for semaphores, for other process communication and everything. So it was nice that the thread library was standardized right from the beginning. And but the point is, in early 2000, I mean, this, you see, most of the desktop computers have only a single core CPU, and there is no support for hardware threads. There's no point of having. So it was almost a like a theoretical concept, and it was never realized in practice in that form. But it was proposed, and the implementation came in the mid 90s. And in 2002, Intel added a support for simultaneous multi-threading to Pentium 4 processors. And it was the time, I mean, we have already joined our jobs and all, but still it was in a very nascent stage under the name hyper-threading. But in 2005, the dual-core Pentium D processor, and so there are many multi-core processors which are affordable to desktops and for the normal users. Earlier it was affordable for the servers only, but now, and once this was there, from the mid 2000, this threading concept became very popular, because even a in your desktop, or these days even the mobile phones, processors, they are having multiple cores. So you can really exploit the presence of multiple cores, and you can, if you write a multi-threaded application, it really makes sense. And that's why the popularity of multi-threaded applications started almost like 10-15 years. It was very popular. Hello. So can you interpret this figure? So in the first case, you see the box represents a process, and this curvy line, it represents a thread, execution thread within that process. So the first one, what is the example of that? What kind of system resembles this case?
Single
So
core.
yes, no, there is no concept of core. Core means is a physical CPU is called as a core. Okay, I'm not talking about the core. My point is in terms of the operating system. In terms of the operating system, this means there is a single process, and within the single process, it can sustain only one single thread. Okay, so if it is restricted only to that, so earlier the MS-DOS operating system that was mainly developed for providing or providing OS support to the desktop machines in those late 80s and 90s. So those MS-DOS operating system, they actually came up with this philosophy because they didn't bother about creating multiple threads or even multiple processes uh, to us. I mean, user processes to a large extent. Now, what is this? But parallelly, in the servers, the Unix servers, traditional Unix servers, they supported multiple processes, but each process supported a single thread within it. Right? If you prefer to call it as a thread. So those are those primitive Unix in the early 80s or the mid 80s. Now, somewhere during 90s, Java runtime came, runtime environment, and that supported that a single process will have multiple threads of execution. Okay, so one process and multiple threads, but Java will not allow you to create multiple processes independently. It's like for, but one process, but it will, you can create any number of threads and all. So this schematic will, uh, you know, this is something similar to what we get in Java runtime, and this is the extreme case where you can have a support for running multiple or creating multiple processes like the boxes, and within each process you can have the provision, you can have the suitable function calls or system calls to which you can create multiple threads of execution. So this is the extreme. So this is one extreme, and these are the other extreme. And this is what the Linux and all these kind of operating systems do support. In fact, all the modern operating systems, multitasking operating system, multi-programming operating systems, they support creation of multiple processes, and within each process you can have multiple threads created. Is that fine?
Yes, sir.
Yes, sir.
So now there are some simple examples of multi-threaded applications, and these are more or less easy to understand. So it's like web server. If I consider a web server, so web server, what happens? Web server is if this is a web server machine. So web server is a machine, and in this machine you have got what you have got, say HTML pages, right? Or I mean web pages, you can say. And each of these web pages, they can have hyperlinks to other pages. So this will link to this like this, and this will link to this. So this is, so a web server uh, uh, generally hosts a set of interconnected hyperlinked web pages, right? And there are some remote machines, and if they are connected through the network, so if, so these machines can make requests. So maybe through the browsers they will make requests to fetch any. So if I, and each will have some address. So if I want, I can make a request to fetch this particular page, it will be brought to me. This user can make a request to fetch this page, it will be brought like that. So this, in this web server, what are the different tasks that you need to perform? Now it may be a very large web server, I mean consisting of several hundreds and millions of web pages. Okay, it has hosted, and it can probably, and it should be able to receive and serve multiple such clients, like, so these are clients and this is web server. Now the thing is, the web server does not know how many clients will be connected to it. I mean, will be trying to access the pages from this web server, and it becomes really difficult. Hello, can you hear me?
Yes, sir.
Okay, it says bad quality. Okay, so now to handle this, because you really don't know, sometimes it may be there only 5 clients connect to it, sometimes it can be 2 lakh clients connect to it. So how to deal with it? Now if there is a single process that it creates, if the web server creates a single process through which it need to do the entire task, then there will be a big problem. So a single process means the process is just waiting to receive a request from a client. If it receives a request, then it will see that, okay, if it is a valid request, it will search it through the bunch of pages it has got. If it has got a valid page, it will just initiate a transfer of the contents of the page to this. That's all. Now till that point, if another client makes a request, it will just have to wait, because there is a single process, right? So that single process, till the previous client is served, it cannot go and address the request for the second client, right? Now you say that, okay, if that happens, the web server can create another process. So maybe these are the processes. So this is one process, this is another process. So if there are 3 clients, then there may be 3 processes that the web server can create. Now each of them, so if it is doing so, now the now the point is, apart from search, so this searching logic is the same, then more or less a logical task is the same, but in this case, instead of creating multiple processes to handle this, to deal with the scalability of the system, this web server, a single process can create multiple threads. So instead of this, it can create multiple threads. Okay, so these are thread, these are thread, these are thread. So each thread, whenever there is a client request, a new thread is created. That's all. So new thread is created means it is not as heavy as that of a process, but still it is capable of listening to your request, a new client request, and finding out the page if it is there and transferring the content. And once it is done, it will then close, it will get terminated like that. So wherever there is an overlap in the task and the logic is more or less the same, instead of creating multiple processes, so we can say that this is a multi-threaded web server, and this makes sense, right? So in case of a text editor, we know that whenever you are editing or typing something there are multiple subtasks that you need to perform, like spell checking, keyboard input, grammar checking, then periodic backup, automatically, even if you don't save, after every, say, maybe 1 minute, the contents get saved in the disk, auto saving characteristics like that. So each of these are subtasks. So even when you are running a text editor, instead of dealing with the entire task of text editing in a single process, we can, so the text editor process can create multiple threads, and each of them, they can take care of these subtasks, right? So in case of web browsers, again, when we open the web browser, say Google Chrome, we know that there we can open multiple tabs, and one tab may be displaying some dynamic content, one tab it is downloading something, one tab you are searching. So you are basically performing multiple different tasks in the in the web browser. So instead of having a single web browser process, which definitely cannot handle all such functions, activities of a tabs, of different tabs, and instead of creating a separate process corresponding to each tab, it is always better that the web browser process creates multiple threads, and each thread takes care of the activity in a particular tab, right? Hello.
Yes, sir.
Yes, sir.
So
Yes,
then in
sir.
the computer games also, these are pretty obvious, because there are different objects that you actually deal with in a games. So different objects, the movement of the object, the change of the shape, or whatever the action to be taken in the object. So whenever there are different object is created, so that object, for that object to handle the activities of that object, as create a thread. That's all. So you can really exploit uh, or make things faster if you create a separate object, or maybe you can have a thread dealing with, or tackling a class of objects, uh, gaming objects. video encoders, the video is a collection of different a collection of image frames, right? Time tagged image frames. Now encoding, when you think of video encoding, so each frame need to be encoded separately. So we can create a separate thread where each thread encodes a particular frame in that video stream, right? So there can be many such applications of multi-threaded application scenarios. Okay. So now can you see this diagram?
Yes, sir.
So can you interpret this? Now you see, now the point is, this is a kernel space, right? This is a kernel and this is a user space. Now here you see, in the kernel space, say this is a process, and in the user space we have got a thread library, some utility through which this same process has been. So what I mean to say is, in the user space, you created multiple threads of execution. I mean, it is the user's way of solving the problem. But it may be that in the kernel level, still the kernel knows there is a single process. Are you getting my point? So if you ask the kernel how many processes are there, the kernel says there is a single process I have created. How many executable units? The kernel says there's just a single executable unit, right? But in the user level, using some user level library, you can say that I would create separate threads of that process for execution. But in fact, they are not all visible to the kernel. They are only visible in the user level. Are you getting my point?
Yes, sir.
So what I see that, what are the types of threads? So the basic why thread is required we found. Then what things should be common in multiple threads we found. What are the applications we also discussed about that. When during what time, in the OS evolution, the thread concept came and how it matured, that also we got some idea. Now the thing is, what can be the possible implementations of, I mean, when you design a multi-threaded library, so how can you implement it? What can be the type of what are the choices that you have got? So see this analogy. The analogy is that academic section, this BTech third year. Do you know that what the academic section? If you ask the dean, do you know what the dean they record or they maintain in of their own? In this BTech third year, CSE third year, we have got three sections, right? CX, CY, and CZ. Do you think that the dean academic, he is aware of having the three sections? In your case, hello.
No, sir.
So they are not aware. So they says that you are running a BTech CSE batch, right? Fine. And we are saying that okay, this is so this is a batch, and they are studying this OS and all this. So do whatever you want. Now it is up to you. If you find that okay, the classrooms are not big enough, and you have to divide the entire batch into 3 or 4 or maybe sometimes 2, it is up to you how many sections you want. Sometimes if the intake is less, you say that let us do it in 2 sections. So it's up to you. Now the division of the sections is entirely the task of the CSE department and the departmental academic committee DAC, and this whatever is done is not visible by the academic section. Okay, whenever they ask for the marks, we say we compile all the marks from CX, CY, CZ and we pass it on to them. Now who took it, like whether it's a single faculty who takes all the 3 sections, or there are 2 faculties taking the 3 sections, or how we are managing, they are not at all bothered. They say that we want to get the marks for total 180 students of the CS third year, that's all, for a particular course. And how you are organizing the classes and all this, we really don't care about. Okay, so this is one extreme, and this is called user level threads, because the presence of threads is felt only in the user level, and it does not percolate vision, it does not percolate to the kernel level. Is that fine?
Yes, sir.
So is the analogy clear? Now this is another extreme. Can you decode this? Now what we have, so yeah, for the third year it is fine, but in the first year, in the first year and the sorry, in the first year, in the first semester and the second semester, do you know what happens? So in the first year and the second semester, irrespective of the departments, you have got common courses, right?
Yes, sir.
Yes, sir.
So the entire first year students are divided into say 8 sections, say AXY, BXBY, CXY, DXDY, like that. Okay, and then so now who does it? That is done by the institute academic section, and they say that okay, maybe AB, AXAY, BXBY, they will be doing the introduction to computing this time. So now the CS department, so the existence of the sections are visible, are actually done by the academic section, and they are visible to the individual department also. Can you see the mapping?
Yes, sir.
And same holds. So simple analogy is here, the kernel, the so there is through some kernel level API or through some system call, you have got, so through some kernel level system call, a process creates different threads. Okay, and because these threads, the existence of the threads are visible and maintained in the kernel level, kernel space, we call it as kernel level threads. And obviously these each kernel level thread is also visible in the user level. So if the presence of the thread is known and maintained in the kernel space, it is called a KLT, kernel level thread. If the presence of the threads is known only in the user level but not in the kernel level, we call it as a ULT, user level threads. Is that part clear?
Yes, sir.
And what about this one? Can you decode this? Focus in this particular. So seventh semester, you see, a process creates a single thread, and that is also visible in the user space. But for some other year, say maybe first year, a process like a particular batch is created into two sections, AXAY. Now this AXAY, when it is asked to take the class, when the CSE department is asked to take the class, they says that AXAY is also too big for us. So they can make further divisions. Maybe AXAY, they will merge them together and they will say that we'll take the classes in three separate sections, A1, A2, A3. Is that clear?
Yes, sir.
So the point is, the presence of the threads is visible in the kernel level, in the kernel space, and also it is visible, definitely it is visible in the user space. But the thing is, there may not be a one-to-one mapping. You see, in the previous case, it has got one-to-one mapping. One kernel thread is interpreted as a user level thread. So this kernel level thread is, one kernel level thread is visible as a user level thread, each of them. But here what happens, multiple kernel level threads may be mapped into few or more user level threads.
Many to many.
Hello?
Sir, many to many mapping.
Yes, many to many mapping. So if you would like to implement hybrid threads, and because of that they are called as combined ULT KLT approach, which is called hybrid threads. And so you should have a provision or rule to say that okay, I have got this say I have got 10 kernel level threads, and in the user level I would like to map it to say 4, maybe groups of them, and then they are created accordingly. And then what is the policy and what should be the logic behind, and that is different. I mean that differs, and that is more of a design issue, but then the facility is there. Okay, so here can you say which of these three, one, this is ULT, this is KLT, and this is say combined approach, which of these three will be able to exploit the presence of multiple cores, CPU cores? This one, this one, or this one? If you really have got a multiple course, CPU course, which of these will be useful?
Sir, many to many.
Sir, ULI and hybrid.
KLT?
Many to many mapping, sir.
Yeah, this is obviously fine, but what about this one? If I have the KLT option, will it be able to exploit the? It can, because you see, you know that the kernel knows that there are multiple threads, and you can write a scheduler which will schedule these threads, right? Here also, you can write a scheduler which will schedule these threads. But in this case, the kernel is not aware of multiple threads. So the kernel is scheduling either this process or, I mean, just a process. So if you have ULT, can you exploit the presence of multiple cores?
No, sir.
No, sir.
So got this point? Got this point?
Yes.
But what is advantage here? Advantage, you see, the thread switching. Thread switching means if the execution need to switch from this thread to this thread, so it becomes very easy because you don't have, so switching of execution from this thread to this thread, does it require a context switching? I mean, kernel level context switching?
No, sir. Part of the same process.
So it's in the same process. So in true sense, I mean, process context switching is not required here. So this becomes, in that sense, this becomes really lightweight, right? This is really lightweight. And scheduling, but the problem is the scheduling can be application specific. So you can have a application specific policies for this, and ULTs can run on anyways, because you are not changing anything in the kernel level. So it's just a user level library which will create multiple threads and try to utilize the benefit in some form. So they are really portable. Okay, but the basic inconveniences are most system calls are blocking. So now the thing is, if this particular thread, you see, this particular thread goes into blocking, that means a whole process will be blocking. So you cannot, probably it will be difficult for you to say that or to execute these threads. Are you getting the point? Because if one thread of a particular of a process of a user level process, one ULT of a particular process is getting blocked, the OS knows that, okay, this process is blocked, that's all. So it cannot exploit the parallelism into that extent. And here the kernel can only assign processes to processors. So two threads within the same process cannot run simultaneously in two processes. Even though you have got multiple cores, you cannot exploit the advantage. In this case, definitely the advantages are it can simultaneously schedule many threads of the same process as on many processors. This is possible. Blocking is on a thread level, not in a process level, and kernel routines can be multi-threaded. So what I mean is the kernel itself, the kernel modules can also be multi-threaded. So the kernel itself runs multiple modules. So you can have a multi-threaded kernel, which is faster and also much more efficient uh, than a kernel which is not uh, aware or implementing multi-threaded concept. But what is the major inconvenience? The thread switching becomes, in this case, it involves the kernel, and that's why it is slower. It is, the overhead is more. Hello?
Yes, sir.
Yes.
In the hybrid case, so it will basically combine both of it. Okay. And the hybrid, this hybrid one is, this is lightweight. There is a concept of lightweight processes, and we can just get into those. There are some codes that I would like to show, but I think better I stop here today, and tomorrow I'll take a class in the first half, and tomorrow we'll be talking mainly about the thread codes using clone function and all. We'll be focusing on the implementation. Okay, so these codes we'll see. Today I got late, so anyway, so it's better we have got a basic idea of the threads, and tomorrow we'll focus on more detailed discussion. So do you have any question?
No, sir.
Okay.
Sir,
So I
can
think,
you,
yes.
sir, can you please mail us this video recording because we can't access this?
Yes, definitely that I'll do. I don't know whether it has been recorded. But I think it will be. It would have been recorded. I'll pass it on. Okay, so tomorrow I think we have got a sessional in the second half, but I would like to complete this threading in some theory class in the first half. So when can when can I take the class? A 1 hour class is good enough to complete this portion, so that you can do a bit of coding. You can focus on coding aspect during the lab hours.
There is 12 fine,
হুম
12 p.m.
শুনতে পাচ্ছি না।
So 12 p.m. sir, 12টা.
12. Okay, from 12 to
1.
so 12 to 1 if I take, then when is the lab schedule?
Lab is from 2 sir. 2 to 4. Sorry sir, 3 to 4.
3 to
3 to 5. 3 to 5.
3 to 5. Okay, so fine, then I'll start from 12. If possible, can it be started from the 10 to 11? Do you have a class?
Yes sir,
I know
it's
the late
possible.
risers will not agree, but is it possible?
Yes
10
sir,
to
it is
11?
possible.
yes, sir.
All others agree, so that there will be some bit of gap also, and I'll be able to do some official work also in between. So from 10 to 11 I'll take the theory, and then from 3 onwards, it will not be from 3, okay, I'll let you know from 3 or maybe 3:15 I'll start the lab. Okay, and I'll pass on the assignments also on this. So I'll complete
Okay,
this threading by tomorrow, I guess, and then afterwards I'll start this shared memory, and followed by the process synchronization semaphores. Okay, if you don't have any questions, then I can leave.
thank you, sir.
Thank you sir.
Thank you.
Thank you, sir.